Welcome to lecture number 40 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done up to this point. So, up to this point we have studied the material nonlinearity, first considering uniaxial stress strain response, and then we have looked at this cross section level, okay? And then we have looked at the plasticity theory for multiaxial state of stress, okay? And then we have seen how the plasticity theory can be made useful to study PMM interaction, okay? So, all that discussion was either at the material level or at the cross section level, right. Now, we would like to move on to the element level, so that we can model a structural system, okay. So, therefore, in this topic we will be talking about the concentrated plasticity approach for modeling lateral load resisting systems, okay. So, first I would like to spend some time on lateral load resisting systems for seismic loads, and then we will talk about the concentrated plasticity approach. Okay. So, as you know, any structure is made of structural as well as non-structural elements. Okay. So, and I am sure all of you are familiar, so I do not have to get into which are structural elements, which are non-structural elements. And structural elements must be designed to resist both gravity loads and lateral loads. So, gravity loads are dead, live, snow, etc. Okay. On the other hand, lateral loads we have primarily wind load and earthquake load. Okay. Now, based on the transmission of these two types of loads, we have two different systems that carry this load. One is called the gravity load resisting system. So, in a building structural system, we can have dedicated system for carrying only the gravity load, and then we can have another system which is dedicated for carrying the lateral load only, and this lateral load resisting systems will also carry some part of the gravity load, that is fine. Okay. So, how are the lateral load carrying system work, or for earthquake excitation, how the lateral resisting force system actually develop the forces. So, here is an example or a picture that demonstrate. So, as you may be knowing, the earthquake is a ground shaking, right. So, you have a building and the ground below is shaking, right. So, it develops the building at each floor level develops the inertia forces, which is shown here, right. Now, these inertia forces through the floor diaphragm gets transferred to the vertical elements, okay. That could be a shear wall, could be a moment resisting frame, could be a breast frame, and so on. So, these elements are called the lateral load resisting system. They transfer the forces to the foundation. Okay. So, what are the different types of lateral load resisting system we can have? We can have in reinforced concrete building moment resisting frame, structural walls which are also called shear walls, and a dual system which is a combination of the two. Okay. When you are using both moment frame and structural wall based on certain or satisfying certain codal provision, then you can call it a dual systems. Okay. I am not getting into the design aspects because this is an analysis course. Okay. For steel building, you can have again moment resisting frames, breast frames, steel plate shear walls, and dual system. Dual means any combination of this will call a dual system. Okay. Now, let us spend some time talking about each one of these systems. Okay. Before that, for good seismic performance, a lateral load resisting system must have a minimum elastic stiffness, a minimum strength, and an adequate ductility. Okay. This I have just stated qualitatively because we are not getting into any design in this course. Okay. So, what is a moment resisting frame? I am giving you two examples. One is for a steel which is taken from this book by Talley, and this is reinforced concrete moment resisting frame which is taken from the earthquake tips by Professor C.V.R. Murthy. Okay. So, this frames moment resisting frames basically composed of beams and columns with rigid beam column joints. For analysis purpose, for linear analysis purpose, we take them as rigid, but for nonlinear analysis often the beam column joints are modeled carefully for reasons that we will explain or see later on if the time permits. Okay. Lateral and gravity loads are resisted through axial force bending moment and shear force in both beams and columns that define a moment resisting frame. Okay? The lateral force and gravity loads are resisted through this stress resultant's internal forces, axial force, bending moment and shear force in both beams and columns. And we use in both steel and RC, as you have seen, it is suitable for up to about 20-story buildings. Okay? Beyond that, you have to use different system because this becomes very uneconomical. Okay? Now, let me draw a simple frame. I will just draw a single story frame. Okay? So, let us say this is fixed at the base, this is fixed, and I am applying a lateral force P, and I am interested in the bending moment diagram for this. So, the way I do it, I will say, okay, as if this is unstable, so this will go like so, right? Like I said, as if this is unstable, but well, this is not. Okay? So, this rotation is not permitted here. Then what I should do? The deflected shape should be something like that. Okay? Similarly, here it should be something like that. Okay? And then the beam is going to deflect like so. And now I will erase this one. Okay? So, that is my deflected shape, right. Now, I can draw the bending moment diagram for this. So, the bending moment diagram is going to be, like I said at the beginning of this course, I will draw the diagram on the tension side, though this is tension here, this is tension here. Okay. So, you get a bending moment diagram like so, and here it is like this for the two columns. Okay. And for the beam, to satisfy joint equilibrium, if this is tension here at the beam bottom, it has to be tension. Okay. So, my bending moment diagram then becomes something like this. So, here this is the direction of the curvature, tension outside, here tension inside, this is outside, here for the column it is inside, for the beam it is inside, and here it is top tension. Okay? This is the bending moment diagram, right. Now, imagine this frame is subjected to lateral load. Okay. What will happen? At some point, plastic hinges will form. If you recall our discussion when we started discussing the section analysis, I introduced you to the concept of plastic hinge, right. So, if I apply this load, then the plastic hinges must be forming here at the base, here and here. Now, for a single story does not matter where it forms. Okay. So, let us say at the beams, right. So, this is a mechanism. Okay. So, you get all the inelasticity developing where the bending moments are maximum, right. Now, this was just a simple example of a single story. Let us look at some realistic examples and some more discussion on the behavior. So, here I am showing you a moment resisting frame subjected to lateral load, which is schematically shown like that. Okay. So, if I cut it through any story, okay, then what happens? Well, there will be a shear force like this for the free body diagram above. Okay. So, it is subjected to these lateral forces and these are the shear force, right. So, what will this shear do? So, you will get horizontal shear at any story. This shear forces are in equilibrium with that. That means, the external lateral shear is resisted through the shear force developed in the column. This is one thing, and this shear force causes double curvature bending in the columns with inflection points at the middle. This is what you can see. Okay. And I will show you little bit more in with another sketch. Okay. So, this the moment that is applied, let me first show you this behavior. So, let us say I am drawing this, okay. I am cutting it here, right, and these are my forces, right. So, here you have a column shear like this. So, what it will do? It will cause a bending moment diagram like this, okay. And then below this it is just going to be opposite. So, therefore, you get a double curvature bending, which you have seen in the previous single story case also. Okay. The moments applied to a joint from column above. So, let us say this is the moment from this column above and below, this is the moment, okay. They are resisted by the moment in the beam. So, this is the beam bending moment diagram, this is the beam moment and here is the beam moment. Okay. So, beam also bends in double curvature with inflection points at the middle, which I have already shown you for a single story. So, if I cut this, let us say I am making a cut here at the inflection point, here, here and here at the inflection point, then I get a free body diagram like this. Okay. So, these are my inflection points. Okay. So, this is let us say the applied force here, you will have axial force in the beam, you will have shear force in the column, okay. You will have shear forces in the beam and this shear forces will cause a bending moment diagram like this. So, beam is also going to bend in double curvature. So, you will have this extending like that. So, the curvature is basically reversing, okay, with inflection point around the midspan for beam. Okay. Now, this double curvature bending, why I am interested? This double curvature bending of beams and columns result in a deformation behavior something like this, okay, where it is concave up. That means, if I exaggerate it, it is something like this, concave on the side. Okay. So, this is called racking or shear racking, okay, which causes the horizontal deflection of each flow level and the difference in the deflection between two consecutive flow level is called the story drift. So, because of this shear racking, okay, the story drift tends to decrease with the height. That means, the drift or the difference in displacement in this story versus the difference in displacement in this story, as you keep going up, the story drift due to this shear racking tends to reduce because it is something like this, okay, the inclination basically reducing. So, this is basically called the shear deformation or shear racking, right. Now, how is the bending moment resisted? So, we talked about you apply the lateral force, column is developing the shear force, right, and that causes double curvature bending in the column and consequently in the beams, and that double curvature bending leads to shear racking. But what about if I cut any story, okay, if I draw a free body diagram, let us say something like this, I am cutting any story, I am applying a force here. So, I can always say that if I cut it, I will have a shear force here and it is trying to turn it like so, okay, trying to turn it like this. So, there has to be a bending moment like that. So, this is the overturning moment or the story moment. If you look at the base, it is overturning. At a story level, we call it a story moment. How is this resisted? Well, this is resisted through the axial force in the column. So, this will be subjected to tension, this will be subjected to compression and that is what is shown here. So, this side column is undergoing extension, this is also undergoing extension and these columns are undergoing shortening, right. So, that leads to a horizontal deflection. Okay. So, now here this if you see this is concave down. The earlier case shear racking was concave up, here it is concave down, it is going like this, it is a flexural deformation. Okay. Now, in this case the story drift tends to increase with height, okay, because if I exaggerate it is going to be something like this. So, the drift is increasing with height for the flexural deformation, for shear deformation it is just the opposite. Okay. So, as the height increases, your flexural deformation will dominate, but typically moment frames are restricted up to 20 story because beyond that it is going to be highly uneconomical. So, in upper stories, story drift due to overall bending may exceed that due to shear racking, and bending contribution to total drift does not usually exceed 10% of that due to racking except in very tall and slender frames, okay, which like I said, we do not use moment frame for very tall slender structure. Therefore, the overall deflected shape has a shear configuration for moment resisting frames. Okay. Now, for gravity load, the behavior is something like this. So, like I said, lateral load resisting system will not only carry the lateral force, but they will also carry some gravity load no matter how small it is. Okay. So, let us say the beams are also subjected to this kind of gravity loads, which is dead load and live load. Okay. So, you will have a bending moment like that. Okay. So, these are the inflection points and the bending moment diagram is shown here. Okay. Here the bending moment is going to be maximum at the mid span. Okay. So, this is hogging moment near the ends and this is the sagging moment. The inflection point is about 0.18 L from the ends. Okay. Now, under earthquake condition, if you have done earthquake resistant design, you would know that the philosophy is to accept some controllable damage. Okay. So, under design basis or beyond earthquake, we expect some damage. Okay. So, a properly designed moment resisting frame, how should it get damaged? That is the question. So, there we talk about the collapse mechanism. So, there are two ways a structure can, a moment resisting frame can develop plastic hinges. One is, you have seen the bending moments are maximum at the beam column connection, right. So, in the column here you can have plastic hinges, okay, where the bending moment is maximum, or you can have at the ends of the beam. So, in other words, you can have at the ends of the columns, let us say here, or you can have at the ends of the beams as shown here. Now, imagine if the plastic hinges are forming at the ends of the columns like so, then what happens? Well, this leads to a story collapse mechanism. Okay? As one story can collapse completely and does not lead to much inelastic displacement. So, your ductility reduces, and at the outset I said the ductility is very important for seismic resistant design. So, therefore, this is not a preferred failure mechanism. Okay. What is preferred? We want the plastic hinges to be forming at the ends of the beams. Okay. I mean, for the roof it does not matter whether it forms at the ends of the column or the beam, but for all other floors it must be at the ends of the beam and then at the base of the column. Now, this mechanism will give you a large inelastic displacement as shown and you can get ductility. There is no local failure of a story. So, therefore, this is the preferred mechanism. So, as you can see that the plastic hinges are going to form at the ends of the beam, right. So, can we focus our attention, can we concentrate our attention to modeling this hinge behavior at the ends of the elements, whether it is a beam or a column. For modeling we should do both, we should make sure that there are no hinges forming at the column, unless you model you would not know. Okay. So, with that we will get into the concentrated plasticity approach, but before that let me talk about quickly about the other system also. So, for breast frame you have concentrically braced frame and eccentrically braced frame as I am showing here. Concentrically braced frame means the axis of beam, the column and the braces are meeting at the same point. Okay. Hence, the name concentric. In concentrically braced frame, member forces are primarily axial forces, okay, which I will show. In the eccentrically braced frame, deliberately you create eccentricities. You see this and this are not meeting at the same point. So, you create a link, a horizontal link which is subjected to shear force, axial force as well as bending moment. Okay. And this link is particularly designed or appropriately designed to undergo inelastic deformation and give you ductility. Okay. So, therefore, this EBF shows improved seismic performance over concentrically braced frames. Okay. So, the lateral load path for concentrically braced frame I am just showing with a single load. If you apply a single load and you can analyze it like a truss. Okay. So, these arrows that I am showing are acting at the joint. When it is away from the joint, that means it is tensile. Okay. When it is acting towards the joint, then it is compressive. So, as you can see, these braces are under compression and these are under, these columns are under tension, and whereas these are under compression. Now, you see this is not a good system, because when the force reverses, then this, well, in this case itself, these are all under compression. So, they will buckle. Okay. So, you need to have braces in both directions. This is just showing you how you can analyze and what kind of forces develop in the braces. So, it is primarily axial force, as I have shown in each case for a single point load applied at the top. Okay. Now, if you go back and recall, I said if I cut a story, Okay, I get a story shear and a story moment. How are those two resisted? So, let us say I am applying this, I cut it, I get a story shear like that and I get a story moment like so. How are these two resisted? Well, the story shear is resisted by the axial force in the brace. So, here it is compression, tension, and here it is only tensile one brace. Okay? And the story moment, this is resisted by the couple that is formed through the axial forces in the columns. Okay? That is the mechanism. Okay? So, these are different configuration of eccentrically braced frame. Here the link is at the center, here the link is between an column, between an exterior column and the brace. Okay. Here it is at the two ends, here it is this one. Depending on different architectural requirement, you can have EBF, the link placed in a particular manner. Okay. And then this is the buckling restraint braced frame, which was developed much later compared to the other systems. And in one of the previous lecture, I talked about the idea of buckling restraint brace frame, that is these braces are developed in such a manner that they yield in tension as well as in compression, they do not buckle. We put it within a steel tube and fill this with mortar, and there will be gap between the steel core and the mortar. So, go back to the previous lecture, I think there I explained, or go to this book by Professor Brunet to study more about the buckling restraint braces. So, the behavior of this also I have shown you in the previous lecture. Okay. This shows isotropic hardening in both tension and compression, and it is different. Okay. So, the RC structural walls, you can have wall for steel as well as concrete. So, this I am showing the reinforced concrete structural wall. This has large strength, high stiffness and ductility, and this, let us say if you are using RC wall, then you can design the columns to carry only the gravity load. So, they become part of your gravity load resisting system. Okay. You can also have steel plate shear walls, which are basically you have, these are steel cross section. Okay. And then in between you have plates. Okay. These plates are typically welded to these boundary elements, okay, which we call horizontal boundary element, this one, and this is vertical boundary element. So, these plates are welded, and this is called steel plate shear wall system. Okay. You can install it one or more bays along the full height of a structure. You can use it for new as well as retrofitting of existing buildings. So, as you can see, there are different types of lateral load resisting systems. Okay. Now, this is an analysis class, okay, and it is impossible to talk about modeling approaches for all these different types of systems. So, what I will do, I will give you the basic idea of the two approaches. One is the concentrated plasticity approach, the other one is distributed plasticity approach. Okay. And if you are taking this course for research purpose, you can always read more and extend this to the system that you are working on. Okay. With that introduction, let us talk about the concentrated plasticity approach. So, schematically I can show, let us say we have a beam column element which is part of a moment resisting frame. Okay. So, this is that element that is shown, and as you have seen, the bending moments are maximum at the element ends where the plastic hinges can form under earthquake loads. Okay. So, what we can do, we can model this using zero length plastic hinge, okay, or we can model it using a nonlinear spring. So, that is called the concentrated plasticity approach. The rest of the element remains elastic. So, this is elastic, this is elastic. Okay. Then another approach is we can actually define fiber section along the length of the element. So, this is a fiber section here and so on. Along the length of the element, I can define fiber cross section, and if you go back to my section analysis lectures, we know how to create fiber section using steel as well as for reinforced concrete. Okay. So, you can define it, and then that means the plasticity is distributed along the length of the element. So, this comes under distributed plasticity. Okay. And you can also do a continuum model of an element which looks something like this. Okay. What is this? Well, this is kind of, you can say, a hybrid where the plasticity is spread over a finite region at the end. You give them plastic hinge length. Okay. So, one may classify this under concentrated, one may also say this is like distributed plasticity approach. Okay. So, this I have taken from this reference which I will show you at the end. Now, which model you pick up? Each model has its own limitation. Okay. So, it is a trade off between accuracy versus the computational efficiency. The concentrated models are very easy to use and computationally very efficient. On the other hand, distributed plasticity models are expensive computationally. Okay. For example, this is still okay, but can you actually do a structural analysis model where every beam and column is modeled using 3D continuum element? Okay. Can you create a 3D model like that? No. That depends on the purpose. If you are investigating the behavior of a single member, then probably you have to go for that. But if you are doing a structural analysis, okay, then you can use this one or this one, right. So, depends on the analysis objective. What is your objective? That will dictate which modeling approach you will be taking. Okay. So, now let me focus my attention to this concentrated plasticity approach. So, this is the simplest form of modeling nonlinearity or inelasticity in a beam column element. It is a very efficient approach, and as I discussed, we are concentrating all the inelastic deformation at a known location. Now, I know what is the behavior of my lateral load resisting system. Let us say I am talking about a moment resisting frame, right. So, I know the bending moments are maximum at the element ends. So, I will define my plastic hinges here. So, there are two ways you can model this concentrated or lumped plasticity. What are the two ways? One is through rigid plastic hinge, which is this one, and the other one is inelastic spring. Well, looks very similar, isn't it? So, let me talk about next, and distributed plasticity will take up in the future lectures. So, what is this plastic hinge versus nonlinear spring approach? Well, the plastic hinge or zero length plastic hinge uses the stress resultant plasticity model that we discussed briefly in this course in lecture 38 and 39. We have extended the plasticity theory to PMM interaction. So, which is what is used in the zero length plastic hinge models. Okay. It can include strength and stiffness deterioration, which I have not discussed. It is there in CSI software. But one thing that we have to note, that all this model require calibration to member response data. If you have experimental data, you can calibrate, okay, or if you have equations that are developed based on a lot of research, okay, you can use those equations to calibrate your model. Okay. Now, since I said that OpenSys does not have the stress resultant plasticity model, so I am not able to demonstrate any example, okay. But I would like to point out some relevant research along this line, the zero length plastic hinge, which uses the stress resultant plasticity model. Okay. So, one is 3D beam column element by Professor Powell and Chen 1986. So, these are all listed at the end. Then inelastic link element for eccentrically braced frame. Okay. So, this is like for moment resisting frame, but this is for eccentrically braced frame, that is by Rickles and Popov. Then modeling of non-ductile RC bridge column, again by Rickles. Okay. This all of this use this stress resultant plasticity approach, where the plasticity is confined within a zero length at the element ends. And then this nonlinear beam column element by Eltawel and Deirelin. So, a similar approach has been used by CSI software. Okay. And you can also see the references cited in this paper. So, coming back to the point, concentrated plasticity, there are two ways. One is stress resultant plasticity approach, and the other one is you can use a zero length element as a spring. Okay. For example, let me draw, let us say here I have a column. Okay. This is a column and this is the base, right. So, what I am doing, let us say, let me draw the center line, because we always model using center line, right. So, let us say this is my node 1, this is my node 2, and here I create this node 3. What is the distance here? The distance is 0, right. And then I am defining a spring between this 2 and 3. Okay, and I will be giving the moment rotation response to this spring. Okay, that models my plastic moment rotation or inelastic moment rotation response. What about the axial direction, the shear direction? Well, I can make them constrained with equal degree of freedom, which I will demonstrate in the next lecture. Okay. So, just like I am talking about a rotational spring, I can have spring in each direction. I can have a flexor hinge, which is what I demonstrated. I can have a shear hinge and provide a shear force versus shear deformation. I can also have an axial hinge and provide axial force versus axial deformation. Okay. Then what are this behavior? Well, we have already studied uniaxial sigma epsilon in lecture 15 to 21, and many of those models can be used to define uniaxial force versus deformation, because what I said, so this is uniaxial, this spring is modeling only moment rotation. So, it is uniaxial, it has nothing to do with axial force deformation, it has nothing to do with shear force versus shear deformation, they do not interact. Okay. So, force deformation can also include strength and stiffness deterioration. We shall see some models. Okay. Now, in addition to the models that I discussed, schematically I will show you some models. So, this is a hysteretic model, it has no deterioration. So, this is similar to our bilinear plastic model, right. As you can see, this is similar to bilinear plastic, okay, or Menegotto-Pinto. This model is showing stiffness deterioration. See, this is the initial stiffness and you see the unloading stiffness or the reloading stiffness, they are all deteriorating. Okay. We will not get into this model, but you must know that there exists model that incorporates only stiffness deterioration. This model, what it is doing? It is showing cyclic strength degradation. So, you first cycle you go up to this, in the next cycle the strength is reduced, in the next cycle it is reduced even further. Okay. This is a model that models fracture and strength degradation. So, let us say you go here, something fractures, there is a drop in strength, then it increases again, something else fracture, there is a drop. Okay. So, this is one way. Then this model is with post capping gradual strength deterioration. So, you can see it is deteriorating like this. So, initial is this one, then the next one is that one, right. And then this is with pinching, where you can see as if someone has pinched the hysteresis loop between the second and fourth quadrant. Okay. I will talk more about why do we get this kind of response in reinforced concrete structure. Okay. We will explain that. And as far as strength and stiffness deterioration is concerned, I will talk about a model which is called the IMK model that incorporates both strength and stiffness deterioration. Okay. So, this is just a schematic to show you all these different force deformation response you can assign to individual spring or the zero length element that I was talking about. Okay. So, remember that this inelastic spring approach requires calibration. You need to calibrate the model either with known equations or well established equations or experimental data, and also note that there is no interaction. So, if you have axial force and a moment and you define a moment rotation hinge, the axial force applied and the moment, they do not interact each other. Okay. So, that PM interaction can never be taken into account. Okay. With that, let us summarize. So, in this lecture what we have done, we have discussed some lateral load resisting systems which are conventionally used for earthquake resistant design of structures, and we have started understanding the concentrated plasticity. We have also briefly discussed distributed plasticity, but we will spend more time on that later on. Okay. And we have discussed little bit more about the concentrated plasticity, that there are two ways you can deal with concentrated plasticity approach. One is the stress resultant plasticity and other one is simple inelastic uniaxial spring for each direction that you care about. Okay. In the next lecture, we will solve some examples related to concentrated plasticity approach, and then we will talk about the uniaxial model that features strength and stiffness deterioration, that is the IMK model, and I will also talk about the pinching, why we get pinching in reinforced concrete structure and how we can model that using uniaxial force deformation. Okay. With that, this are the references, these are the next, okay, arranged alphabetically, and this is the final one. Okay. With that, thank you and see you in the next lecture.